I'm Lindsay. Hope you had a good weekend. This is Lab 4, Magnetic Field of a Bar Magnet. The purpose of this lab is to measure the magnetic field of a magnet at different distances and intensities, both on and off of an axis, and to measure the magnetic field using a magnetometer app of a permanent bar magnet, and to gain an understanding of the Biot-Savart law and model a magnetic field using glow script code. For my results, I found n to be negative 4.2498 and the magnitude of mu to be 0.464 newtons per ampere squared. Some physics principles to understand. Firstly, the Biot-Savart law is used to calculate the magnetic field generated by constant electric current, and this is the specific one that we're using for our dipole. And then these two equations right here are both distance dependence formulas, and this first one represents the magnitude of the magnetic field. And then the second one is used to calculate the value of K, which is used to find the mu value. The system here is the bar magnet, and the surroundings is everything else, and some assumptions are that the bar magnet acts as a magnetic dipole, and this is so we can apply our Biot-Savart law, and that there are negligible external forces. Materials are the bar magnet, smartphone, meter stick, magnetometer app, ruler, and some tape and an Excel spreadsheet. And I downloaded the magnetometer app, and then I compensated for Earth's magnetic field by ensuring that the magnetic field of the bar magnet was orthogonal to Earth's magnetic field. I then found the magnetometer chip in my phone by sliding it up and down the meter stick. And then I did this in the perpendicular or the parallel direction, perpendicular, I guess. And then I finally made the measurements requested on the axis at an angle, and then I added these data points to the Excel spreadsheet to give this graph, which the equation of the line will be important in a second. And here's my data if you want to pause and look at it. So for the equation of this line, this slope, it represents n, and n is the power law exponent that tells you how fast the magnetic field's magnitude decreases with distance. Because this is a negative number, we know that as distance increases, the magnetic field gets less and less strong. Although we do know also that this number should be closer to -3 because it falls off at a distance or a factor of r cubed. And then this intercept is the natural log of K, and then you can run through these calculations over here to see how I found K and then how I found mu. Here are my off-axis measurements. I found this as my vector, and I will be ignoring the Z component a little later in calculations. It's not really important here. And some observations is that when the magnetometer is far away from the magnet, it measures the near zero magnetic field in the x direction. And as it moves closer to the magnet, the x component that was measured of the magnetic field increased. Here is my glow script model, and this is for the perpendicular off-axis. And then here I have my mu, again, 0.464 newtons per ampere squared. And then here I have my magnetic field function. I have my representations of my on and off axis arrows of my magnetic field, which show both magnitude and direction. And then here, finally, I just have my magnetic field at 45 degrees away from the axis. Yeah. And so some findings, again, mu of the magnet, we calculated to be 0.464 newtons per ampere squared. Using glow script, we found the magnitude of the magnetic field at 45 degrees to be 1.7507, 10 to the -6th. And for the experimental magnitude, excluding the Z component, we found it to be 8.37 times 10 to the -5th. And these numbers are pretty close in value. Not perfect, but they are pretty close. And the reason that also that the vectors are not completely aligned, the glow script is probably more accurate. I had a lot of problems with the finickiness of the app, and also some more sources of error. The location of the magnetometer chip could not have been perfectly precisely found in my iPhone, and also any electronic or magnetic devices in the surroundings could have affected my readings. And I also could have not moved my magnetometer in a perfectly straight line when taking measurements. So that, in conjunction with the fact that the app was glitching out, led to maybe not perfect measurements and an n of -4. So some discussion questions. If I hadn't oriented my experiment to compensate for magnetic north, and instead I had some intermediate angle with respect to Earth's magnetic field, my results would have changed because the bar magnet's field would have combined with the Earth's field at an angle, which would have led to a skewed angle measurement and inaccurate readings. And if I were to stick two identical magnets together end to end and run the experiment again, I would expect that the effective dipole moment would increase, so the magnetic field would be stronger, but the direction would remain the same as in the first experiment. Thank you so much.